All right, you guys. Hey, so we are going to delve into this magical world that is pH. Now, I know many of you have heard pH. You may have even talked about the pH scale. You may even be such a smarty pants that you can tell me that a pH above 7 is a base and a pH below 7 is an acid, right? Which are all great things to know. But we are going to take this a few steps farther. This being CP chemistry, algebra-based chemistry at that, we're going to get into the quantification of pH. How is that magic number of pH calculated? What does it mean in terms of the types of particles that are present? That's what we're going to do with this lecture. All right. So first of all, what is pH? If I were to ask you the question, what the heck is pH? Right? You'd probably say something about how it measures the acidity of something, right? And you wouldn't be necessarily incorrect there. But we're going to refine that definition. So first of all, again, this might be something that looks familiar to you. You might even be able to tell me certain substances that are acids, certain substances that are bases, and so on. Right? And you could probably tell me that pure water is going to have a pH of right at 7. Anything above that's a base, below is acid, blah, blah, blah. Okay. That's the pH scale. But where we're going to refine this definition is we're going to describe it as a value indicating the abundance of the hydronium ion, right? So if you recall, when we define our acids, in every definition, an acid is something that donates a proton or a hydrogen ion, right? And we also have said that it's not really an acid until it's dissociated into water. So the presence of that H plus ion along with an H2O, right, is going to form hydronium. So it's that hydronium ion that essentially makes something an acid, the presence of that hydronium ion. All right? So pH is a value indicating how abundant that hydronium ion is in our solution. Okay? And so our scale for pH actually ranges from 0 to 14, although it is possible to have pHs outside of that range. It's another topic for another time. Okay? And it is a calculated value. Okay? In that it is on your calculator, right? I refer to that as the negative log of the molarity of the hydronium ion. So by the way, these brackets mean molarity of. Okay? That's an R, not a V. Molarity. I'm going to try that again. All right. Molarity. M-O-L-A-R-I-T-Y. Okay? That's what those brackets mean. So when I say molarity, I'm talking about the number of moles per 1 liter of solution. Right? So if I make 1 liter of hydrochloric acid, the number of moles of hydrogen chloride in that hydrochloric acid would would be my molarity. Okay? And it's pretty much that simple. So when I talk about the molarity of hydronium, how many moles of hydronium are there in 1 liter of that solution? Okay? And all I do is I take that molarity, I go negative sign, log, and then whatever that molarity is, and that'll spit out a number, right? And that number should most often fall within this range of 0 to 14. All right? Now, we'll get into that math here in just a little bit. Let's talk a little bit more about what we mean. All right? So the pH is dependent on 2 primary variables, and those variables are how well it dissociates. So it's like, again, we define this as how strong or weak the acid is, okay? But also how much I put in per liter, right? Or the number of moles per liter. So the concentration, like how much material there is in a liter, that's referred to as often molarity, right? And we define that as moles per liter, like I said. So if I increase my moles per liter, that's going to result in the decreasing pH, right? Likewise, if I increase the strength of the acid, that's going to be a lower pH. Now remember, lower pH means stronger acid. Okay? So if I have a stronger acid, that's going to lower my pH. Likewise, if I put more acid into the solution, so dissolve more in there, increase the concentration, that will likewise lower the pH. Okay? So those are two things that can affect our pH, or how easily it dissociates, plus how much we put in water. All right? Then, speaking of water, if we talk about pure water at 25 degrees Celsius, by the way, we have a pH of 7, and that is defined as a neutral pH, right? So again, many of you guys already knew that we classify pure water as neutral. Although if I do adjust the temperature of water, we can actually change the pH because, of some complicated stuff that we'll get into on the next slide. But again, pure water at 25 degrees Celsius, it should be exactly neutral, or a pH of 7. All right. Now, let's talk about water specifically, and this is going to help us to understand pH. All right. So, when we just have pure water, all right, you guys should know by now that those water molecules, these guys, are moving around, right? And they occasionally collide. Actually, they collide often. Okay? Most of the time, the vast majority of the time, a collision between two water molecules results in two water molecules, right? There's no, really no associated change, right? Now, if I speed those particles up by heating the water, we can make certain more things happen. But occasionally, okay, pure water can auto-ionize, which means it can ionize itself, okay, into a hydronium ion and a hydroxide ion. Essentially, that's an exchange, right? So one of these hydrogens bumped over to there, which is essentially a little Bronsted-Lowry acid-base interaction, right? We have a proton donor, proton acceptor, so this would be my acid, my base, conjugate acid, and conjugate base, right? But essentially, what's important to us is the fact that we are forming hydronium and we're forming hydroxide occasionally, okay? In fact, it's only 1 in every 1.8 billion collisions actually causes this to happen, right? Now, it just so happens that there's so stinking many water molecules in a liter of water that it turns out to be a very large number of hydronium ions and hydroxide ions, okay? Now, let's think about what this causes though, right? So for every single hydronium I get, I also get an associated hydroxide, right? So what we have to understand is we're going back to that Arrhenius definition of acids and bases, right? Arrhenius acids, right, have a hydrogen attached. The presence of hydroxide makes it a base, right? So for every acid molecule I make, I also make a base molecule, and it's a 1-to-1 ratio, all right? And so there's this continuous, in order to form a hydronium ion, I also have to form a hydroxide. There's this continuous balancing act. And so that's why we say that water is neutral. Now, it's not, and it's essentially because of that reason. Now, there's very few, like relative amounts of hydronium and hydroxide in water. The vast majority of the molecules are just H2O, as they look here. Okay, 1 in nearly every 2 billion collisions does cause the autoionization in a hydronium and hydroxide. But the ratio between hydronium and hydroxide is exactly equal. Therefore, the acid-base ratio is exactly equal. Therefore, we say that water is neutral. All right? Now, the natural properties of water, right? The amount of energy required for that collision to be successful and the orientation and so on, at 25 degrees Celsius results in a concentration or a molarity of H3O to be equal to 1 times 10 to the negative 7 moles per liter. All right? And an associated molarity of hydroxide to be equal 1 times 10 to the negative 7 moles per liter. Now, 10 to the negative 7 is a small number. Okay? So that's why I say it's the vast majority of our molecules are just plain old water. Okay? But the way water auto-ionizes creates an exact ratio of hydronium and hydroxide, right? That concentration in all pure water at 25 degrees Celsius is those concentrations. Okay? Because the amount of acid, amount of base is exactly equal, it is neutral. Neither an acid nor a base. Okay? Now, that being said, okay, how do we then turn this concentration into a pH or a pOH? All right? So normally we're going to refer to our pH value, so we'll just begin there. So all I would do, if I know the molarity of my hydronium, right? So in the case of pure water, I know that the natural properties of water, 25 degrees Celsius, will give me a concentration of 1.1 times 10 to the negative 7 moles per liter, right? All I would do is take the negative log of the molarity of the hydronium ion, right, in my calculator. Oops. So I go ahead, put the negative button, I hit log, and then in this case, to get the pH of pure water, I would type in 1 times 10 to the negative 7, which is the molarity of hydronium in pure water at 25 degrees Celsius. And my calculator would spit out this number 7, which is, when we say 7 is a neutral pH, right, that's what that means. Okay, so a pH of 7 means an exact ratio of acid and base existing in my solution, right? So for every hydronium ion, there's an associated hydroxide ion to balance it out. Okay, so when we say a pH of 7 is what exists for neutral, that's what that means. Okay, now let's move ahead. Let's create an acid, right? So a couple mathematical relationships. So first of all, whatever my pH is and my pOH, right? Well, that's just the negative log of the abundance of hydroxide as opposed to hydronium, right? Those two are always going to add up to 14. Likewise, the molarity of hydronium times the molarity of hydroxide is going to come out to 1 times 10 to the negative 14. Now, this is the Kw for water at 25 degrees Celsius. And the Kw is what we refer to as an equilibrium constant. Now, we, in my class, have not talked about equilibrium constants or equilibrium reactions yet, okay? May or may not get to that this year, kind of depends on time. But we just have to understand that this is a constant, okay, for water. So, including when you dissolve something in water, and again, we're assuming 25 degrees Celsius. So, whatever my abundance of hydronium is, okay, even if I add acid to the water, if I multiply that by the molarity of hydroxide, I'm going to get this number. So the reason that's important to us is if I know the molarity of hydronium, right, I can figure out the molarity of hydroxide that's associated with that, okay, because this is my constant. That number doesn't change. So I do very simple algebra to figure that out, okay? So pH plus pOH is always equal to 14. The molarity of hydronium times the molarity of hydroxide is always going to be 1 times 10 to the negative 14. All right, so let's say I give you a molarity of a certain acid, right? How would you go about calculating that pH? So let's figure this out. Let's do one of these practice problems together. I know what you guys are thinking. Hudelberg, this is crazy and over my head. It's really not. Okay, all of you have either done logs or are about to do logs in your math classes, okay? So let's do this. We've got a molarity, right, of 1.00 times 10 to the negative 4, right? So let's say I put just a tiny bit of HCl into 1 liter to make 1 liter of hydrochloric acid. All right? So again, I told you molarity is number of moles per liter, so I'm going to keep things simple and make everything 1 liter for you, since we haven't really talked about concentration and molarity yet. All right? So if we assume that this dissociates completely, and we're going to do that for you guys at this point too, right? HCl is a strong acid. It will completely dissociate. So that means all the HCl will separate into hydrogen and chloride ions. Okay? We can then use these numbers to calculate the pH, the pOH, and the concentration of hydroxide ions. Okay, we don't have to necessarily go in any particular special order here, but let's walk through this. So let's do pH, right? So pH is equal to the negative log of the molarity of hydronium ions, right? So because I put this many moles in 1 liter, that is my molarity. So it's the number of moles per liter. So all I'm going to do is take negative log of 1.00 times 10 to the negative 4, right? I punch that into my calculator and I get a pH of 4. All right? That's simple. I take the negative sign, hit the log button, and I type in the molarity of hydronium that I'm given. And that spits out the number 4 for me in this case. So that means my pH is 4, which means it is an acid. Okay, with a pH of 4. That's simple. Now, we're going to take this relationship. If I know pH plus pOH equals 14, that means 4 plus pOH equals 14. Therefore, my pOH is equal to 10. Boom. pH is 4, pOH is 10, 10 plus 4, 14. Okay. Now, remember, we're using pH values for our pH scale. So a pOH of 10 does not mean it's a base. pH of 4 means it's an acid. Okay? If we look at the pH value to determine acid or base, it's less confusing that way. Okay? Now, the final thing is I want to know then what is my concentration or my molarity of hydroxide ions, right? So that's where we would take this equation into place, right? I know that my molarity of H3O plus is 1.00 times 10 to the negative 4. Okay? Times molarity of OH minus is going to be equal to 1 times 10 to the negative 14. Whoops. Right? So, what do I do in this case? Right? It's a simple algebraic relationship. Right? I want to solve for the molarity of hydroxide. I know that the molarity of hydronium is 1 times 10 to the negative 4. And I know that whatever that number is times the molarity of hydroxide is going to give me this number. So I'm going to divide both sides by 1 times 10 to the negative 4. 1 times 10 to the negative 4. And that means the molarity of hydroxide is going to be equal to 1 times 10 to the negative 10 moles of OH per 1 liter. Right? And that's how we do it. Okay? So, we calculate pH by taking the negative log of the molarity of hydronium. I will often give you the molarity of hydronium, at least I will for now. Right? Or I can give you a really simple calculation to figure that out. Once you know the molarity of hydronium, you can calculate the pH, you can calculate the pOH, and you can calculate the molarity, the associated molarity of hydroxide. All right? That is it. You guys will follow this up with a calculating pH, calculating pH assignment, right? When we've had a little practice with the pH, we're going to do a pretty cool lab called the titration using yellow mustard. I don't know if you guys knew, but yellow mustard has turmeric, which is a pH indicator, right? We're going to do a pretty cool investigation with that. Then we're going to do another miniature assessment for you guys over acids and bases stuff we've been learning, all right? So keep after it. Give this your best shot, and next time I see you, I'll clarify as best I can.